So without further ado, I'll introduce you to Dr. Jack Matthews, who is going to give us quite an interesting diversity of talk tonight, from the origins of life to what's coming next in the Charnwood Forest UNESCO Global Geopark. Over to Jack.
Thank you very much, Graham, and it's a real pleasure to be here as someone who grew up not too far from here and has had the privilege to continue working with black country geologists in the museum at Oxford, like the Civitar brothers and Duncan Murdoch, a former work experience student of Graham's. It's great to be back here to talk today about an area that's been an area that I've researched, but I'm not actually really going to tell you much about my own research today. I'm going to give you a bit of a background about Charnwood Forest, where it is, some of the discoveries that have been made in recent years, and then at the end maybe talk a bit about some of our plans to follow you in trying to turn Charnwood Forest into a UNESCO Global Geopark. And I've got, if you want to know more about that, perhaps we'll bring that out in the questions. There's plenty of, I've got some spare slides just in case you've got any questions about that. So when we talk about Charnwood Forest, where do we mean? Well, we're in Leicestershire, and I've got a map there on the left-hand side. It's about 150 square kilometres. So that's just under 10% of the county of Leicestershire. We're the coloured-in region here, and we sit between Leicester in the southeast, Loughborough in the north, and then the historic coal mining towns and villages of Colville and up into Thringston. So this is the old northwest Leicestershire coalfield here, just outside of the geopark. And you can see I've put up on the right hand side there a simplified geological map of Charnwood Forest. In those kind of browny pinks there, that's the Triassic. We are not short of a bit of Triassic, and it forms most of the low-lying areas, but popping up in between those areas of Triassic are many different rock types. All we need to take away there is lots of different colours, lots of different rock types, most of them pre-Cambrian, but we do have a few other things as well. So even in a relatively small area, much smaller than the Black Country Geopark, lots of different rock types, most of them pre-Cambrian. So what I'm going to do now is just give you the brief overview of Charnwood Forest, its geological history, and how it has evolved over the last 600 million years. Because we don't actually have a good age for the oldest rocks in Charnwood Forest, but it would be reasonable to assume that there's something around 580 to 600 million years old. And during that time, Avalonia, which I'm proud to still be standing on now, the small microcontinent of Avalonia, which links together southern Britain with eastern Newfoundland, parts of Nova Scotia, and also parts of the Low Countries. All of that would have been somewhere in the southern hemisphere, probably similar latitude to modern-day Santiago. And that would have been an island arc setting. So we've got to think like the island arcs of the Caribbean, but not quite so tropical. And we also have to remember we're just coming out of the last of the snowball Earths. So the 580 million years ago, in some parts of the world, we were getting the third, maybe, snowball Earth at this point, what's called the Gasquier's snowball Earth glaciation, with the Sturtian and the Maranone being even older than that. So climate was doing very different things at this time. But we're in the sea. We're in the sea off an island arc setting somewhere in the southern hemisphere. And so we've got our volcanoes bringing in ash and other volcanic rocks, and we've got sediments at the bottom of the sea. And these are our typical Charnian rocks that Charnwood Forest has become so famous for. And there's a little fossil friend there living at the bottom of the sea, and we'll talk more about the fossils in a moment. Now, the dates that we do have are from airfall tuffs, which then fell into the sea, percolated down through the water column and smothered the fossils that were found there. Luckily, within these ashes are also plenty of zircons, which we can use very high precision uranium lead dating. And so it's through the work of people at the British Geological Survey, Steve Noble and Dan Condon and colleagues have given us the very precise dates that we have, particularly for the fossil-bearing section. So while we don't quite know how old the very oldest is, the fossil-bearing sections are now very well constrained litho and chronostratigraphically now. So we know that they are somewhere between 560 and 570 million years old. And I'll go into that a bit more when we get onto the fossils. So we've got our layers building up in the ocean, pretty typical, at times turbiditic sediments. We also have some superb deep marine slump structures with contorted, semi-lithified pieces of sediment that as big as a mattress and then rolled over and even rolled in on itself. We have a structure at Bradgate Park which we refer to as the Swiss roll. You must imagine the amount of energy you must have had flowing down the slope at that time to take semi-lithified pieces of sediment as big as a king-size mattress and be rolling those up to give the lovely contorted sediments we now see in places like Bradgate Park. And this is how we're forming our Charnian rocks, and of course they're interspersed with volcanic ash layers. And then into that we also know from the relationships that we see in some of the outcrops like Cliff Hill Quarry. We can see the direct relationship between the South Charnwood diorite and the Charnian rocks to know that these diorites were intruded into those sediments. South Charnwood diorites, you might have come across those by a different name, also known as Markfieldite. Indeed, that's after the local village of Markfield, where one of the older of the quarries that quarry that rock was found. And what you will find, so well known was the diorite at Markfieldite, that some authors, particularly around the end of the 19th century, referred to diorite anywhere as Markfieldite, even if it was a true diorite and not, the truer, more inclusive term diorite. They would just say Markfieldite. So it's something to just keep your eyes open to if you're doing any historic geology, particularly in the British Midlands. If you see the word Markfieldite, really, it's just someone saying diorite. And we know because of, there's a structure we see in here. This is a very characteristic rock, Markfieldite, very easily recognizable. We're looking for an igneous rock with pinks, greens, dark greys. We'll find it was, as I'll talk about in a moment, quarried a lot and used to make curbstones in Victorian England. So you can find it in Wolverhampton, Birmingham, Leicester, Nottingham, Oxford, London, all around the country. This was used for building, and that speckledy pink, green and grey rock you can find everywhere and very easily recognisable. And part of that speckledy appearance is caused because in that South Charnwood diorite is and this is your igneous petrology bit for the day, it has a granophoric texture. And as someone who's not an igneous petrologist, I simply explain that as rather than having euhedral crystal boundaries, we've got interfingering phases in the crystallography. And that's mainly between the feldspars and the quartz interfingering. And if we look on a thin section, we can see these lovely wiggly patterns. And people cleverer than I tell me that that means that that granophoric texture is telling us that the South Charnwood diorites were intruded at a shallow depth. So they are true intrusive igneous rocks, but it was at a shallow depth, and they were intruding into sediments that were still wet. So that's telling us a bit more about what's happening in this time. So let's summarise that up. We've got our Charnian supergroup, our Ediacaran rocks. Ediacaran being the most recent part of the Precambrian, 635 to 539 million years ago, named after a farm in South Australia, a couple of hours' drive outside of Adelaide. And the most recently named geological period in the stratigraphic guide. And then we've got our big blob of South Charnwood diorites there. Of course, actually, there were many of these intrusions forming a line down the western part. And we've got our sea there. And we know at some point between the late Ediacaran and the early Cambrian, there is, unsurprisingly, because you see this all around the world, in most places, there's an unconformity. And we know from the work of Duncan McIlroy that was done in the 90s as part of his doctoral thesis that this erosive period must have what we call unroofed the top of the Markfieldite. Because in the lower Cambrian unit that follows, we find bits of the Markfieldite. So that's telling us we must have had some erosion at that point. We've unroofed the Markfieldite and we're finding bits of it in the Cambrian. We've got a number of Cambrian units, some of which are only found in very, very few places, but probably the one that we're most well known for is the Swidland slate. The Swidland slate of the Brand group. This is used most prominently to make gravestones. So many gravestones in Leicestershire and Nottinghamshire are made of Swidland slate, and they can be beautifully carved with very ornate detail. And part of it is because they're so heavily bioturbated. So we find a fossil in there, a trace fossil called Tyche ignis, which is very useful because it can be used as a stratigraphic marker. So we know which part of the Cambrian we're in. But all that churning from these wormy-like creatures in churning up and making that Swidland slate, rather than being actually parallel laminated sands and silts, that all got made beautifully homogeneous for the most part. And that's why it can be carved so beautifully. And it preserves very well as well. And it's interesting, you go into a graveyard in Leicestershire, and perhaps I'm making too many assumptions here, but you find a gravestone from the 19th century, and it's made of Portland stone. And I make the assumption there that that's someone in Leicestershire who's gone, I'm going to import something down from Dorset. That'll be very nice, won't it? You know, someone who's thought that the real person has a Portland gravestone. Their gravestone can't be read anymore because it has frittered away, whereas the proper local Swidland slate is still there. You can read every word of it and the ornate detail of the carvings as well. But it was also used to make all sorts of weird and wonderful things. Obviously slates for roofs. Most of our historic buildings in Leicestershire have Swidland slate roofs, but also everything from gate posts to cheese presses. We're quite well known in Leicestershire for our cheese, and many cheeses were pressed on Swidland slate. Very easy to make and also very easy to keep clean. So yeah, we've got cheese stones made of our rocks. So we've got our Cambrian, and we've got our Charnian, and we've got our also our Precambrian diorites. And then sometime, probably late Silurian, this all gets squashed. And that's how we get the great fold that defines the shape of the outcrops we see in modern day Charnwood Forest. Also, at some point, probably the Ordovician, the Mount Sorrel granodiorite is intruded into this as well. So we've got some Ordovician rocks as well. And there are still some undated dikes and sills that cut through the rest of it that are undated. So one of the things I like about Charnwood Forest is there's still a lot of questions. So if we've got anyone in the audience who wants a little project to come and do a bit of geochronology or some petrology, and there's still questions to be answered in Charnwood Forest. And then what happens during the Permian, as we see across most of southern Britain, is a relatively erosive period. At this point in time, Charnwood Forest, like most of all of southern Britain, is pretty near the centre of the supercontinent Pangaea. We're somewhere around an equatorial latitude. It's probably rather hot, but during the end of the Permian, that's when we've got a very erosive period, and that's when the landscape of Charnwood Forest is sculpted. The landscape of Charnwood Forest is not recent. It is at least 250 million years old. And all that has happened is it's been covered up and re-exposed a few times. And really, the shape of the hills and the valleys of Charnwood Forest is pretty much defined by erosion during the end of the Permian, roughly 250 million years ago. And during this time, we also get not only the carving of the Charnian rocks, but also those intrusions, those igneous intrusions are exposed again and eroded, and we get the typical what's called a Bornhart a geomorphological feature. So these are often when we have very hard rocks like markfieldite, igneous rocks, and we erode them through wind processes, we get curved topped features with very sharp sides. So that's what we got in Charnwood Forest during the end of the Permian. And then while we're still in that, in Pangaea, we cross over into the Triassic, and we're still in those very hot environments of the Triassic, but we switch from being erosive into depositional. And all the valleys start to get filled in, mostly by a mixture of wind-blown sediments, so we're getting dusty, sandstorm type environments, but also flash floods. And many of the geologists who worked on understanding this landscape, their thoughts on this were shaped by their own visits and what they had read about places like Saudi Arabia and Oman, where structures like this, valleys that had wind-blown sediments in them but also had flash floods, they're called wadis. And so you will find in the geological literature the paleo valleys of Charnwood Forest are often referred to as the wadis of Charnwood Forest. And we can still see these structures today. I showed you the map earlier on with the Triassic covering most of our area. Of course, just like in the West Midlands, in the East Midlands, we tend not to get huge amounts of outcrop of our Triassic, except where people have dug a hole in the ground or made a road cutting or something like that, because it's forming mostly the flat parts of our landscape that are quite good for farming. Now, of course, what we've done in Charnwood Forest over the past 2,000 years is dug quite a few quarries, and these have created brilliant outcrops of the unconformity between the Triassic and the underlying Precambrian or Cambrian. So we've got our unconformity there with, more than 250 million years of missing geological time between the Triassic and the Precambrian. And we can see those structures in glorious detail in some of our large quarries. And they really are spectacular. If you look at the faces of the quarry in Barden Hill, you can see, I hope I've got a picture coming up, you can see a cross-section through an ancient valley that in the modern day is more than 300 metres wide and probably getting on for 100 metres deep. And you can see all the detail in that beautiful V-shaped valley. You can see how it's been eroded into the Precambrian and then filled in with the layers during the Triassic. So post-Triassic, through various periods of erosion, we merely shave off most of the Triassic. And of course, as we get out of the upland area of the strong, robust rocks of Charnwood Forest, you get these, the plains of the East Midlands, certainly to the south and east of Charnwood Forest, which are dominated by the Triassic. And those bits of Triassic inside Charnwood Forest are hugging those ancient valleys. And where you stand on top of a hill in the modern day, so whether you go to Beacon Hill or Braggate Park or any of these places, you're actually just standing on a hill that was a hill during the end of the Permian. And it's been buried a bit and then re-exposed. And I think that's a wonderful story that we can share with people about the cyclicity of geological processes, but also the fact that not everything you see, there are some geologists who will tell you all topography is modern. And I would say that sometimes I think the story is a little more poetic than that, because really our topography is ancient and it's merely been covered up for a bit and certainly during the Quaternary re-exposed. Now I'm sure it's important to give the background, but I'm sure you probably know Charnwood Forest most well for its fossils. So I'll tell you a few tales of our fossils. So on the left-hand side there, we have the holotype, the original specimen of Charnia masoni. That specimen is 21 centimetres long, and for conservation reasons is now held in the museum in Leicester. And you can go and see it if you like. If you go to the Leicester Museum, it's there for everyone to see. That specimen was discovered by two separate people, both of them school children. The first in 1956 was Tina Negus. She found this fossil and she went and told her teacher in school that she had been out in an old quarry in Charnwood Forest and that she had found a fossil. And her teacher told her that she couldn't possibly have found a fossil because Charnwood Forest rocks were known to be Precambrian, and everyone knows that there aren't fossils in the Precambrian. Stupid girl, off you go. 1957, 1 year later, Roger Mason finds exactly the same fossil. Roger goes into school and says, I found a fossil in Charnwood Forest. But the main difference was Roger had a family who was connected into the university. And so there was that little bit of extra persuasive power. And they showed some drawings, and one of the professors agreed to come and have a look, who was at the time still incredibly sceptical. At this point, there had been no confirmed complex fossil from the Precambrian. There are a few people who claimed Precambrian fossils in Newfoundland, but by this time they had been incorrectly ruled as concretions. So Elkanah Billings actually discovered the first Precambrian fossil behind the modern-day post office in St. John's, Newfoundland in the 1880s. And then everyone said, no, it's not a fossil. And then in the modern day, we've all gone, oh, actually, it was a fossil. So that's really, but at this time, no one had found anything in the Precambrian. William Salter had suspected he'd found a few things in the Longmindian. We now know them to be raindrops, the impressions from raindrops. And this was really part of what's referred to as Darwin's dilemma. So if you go and read The Origin of the Species, I think it's chapter 9, but I might have got that wrong. He talks about, if my theory be true, below the rocks where we find what we now call the Cambrian explosion, Darwin was saying there must be something below that. You can't really have a Cambrian explosion and nothing before it. And Darwin's saying in his wonderful way of recognizing the holes in his own argument, he's saying there must be something before the Cambrian, but no one's found it. And he actually writes about Salter's potential discoveries. But up until the 1950s, no one had got anything that everyone was happy with. And so that's why this find was so doubted at first, and then because of those connections, Roger Mason finally manages to get someone from the University of Leicester to go out. They have a look, and I mean, you see that, and you think, that's a fossil. You know, I've been a Precambrian stratigrapher and paleontologist. I deal with a lot of stuff where we can have a legitimate argument about whether it's a fossil or just a blob on a rock. But you look at that and you go, that's a fossil. So they knew once they'd seen it, that it was indeed a fossil, it gets written up, it gets published in Nature, and everyone's like, ooh, all those rocks we never bothered to have a look at could have had something in. And this kind of triggers a bit of a kind of paleontological gold rush around the world, because everyone realizes our assumptions are all wrong. There can be fossils, and large complex fossils, in the Precambrian. And so it was no surprise that later on in the 50s and in the 60s, Precambrian and particularly Ediacaran fossils start to be found all around the world. In Canada in 1967, there were also the discoveries in Namibia and in Australia, and we start to build the picture of the Ediacaran biota that we know today. And yet, from that initial discovery in Charnwood Forest in 1956 and 1957, Charnia has now gone on to be found in Australia, Canada, China, and Russia. Incidentally, Tina wasn't really recognised in this story until much, much later. I think it was the 1990s. And a TV programme was made telling the story of how the schoolboy from Leicestershire had gone and found the Charnia fossil, and then it had been written up by the esteemed professors from Leicester. And she's watching this programme on the TV in the 90s and going, that's my fossil. Quite understandably so. And from that precipitated a number of discussions, and I think it's a mark of the man that Roger Mason is, that he quite rightly recognises that this is a joint discovery, because it's almost certainly the fact that part of it is the play of the luck of having the connections into the university and being able to knock on the right person's door. But I think we also shouldn't shy away from the fact that Tina was probably dismissed because she was a schoolgirl, and it's quite wrong that that's happened. So I think it's really nice to see that it's recognised now as a joint discovery between them both. And I know that people in the UK paleontological community are also working on making sure that Tina has a fossil named after her, because of course this is called Charnia masoni after Roger. But there will be Tina fossils on the way as well. It should be said that it's a great example of the impact that being involved as a child can have as well, because the other part of the story is that Roger Mason goes on to study geology and become a professor in geology. So it's nice to think that that might have been started by finding this fossil. It also, we should say, topical with things going on in the news and on the telly at the moment, that this I think it's okay of me to say perhaps annoyed David Attenborough a bit, because David was in the same school as Roger Mason, and I think was 1 or 2 years apart. And Attenborough also loved to explore the geology of Charnwood Forest, and so certainly he's spoken online about how wonderful it was to have someone in his school having found that fossil. But wouldn't it have been nice if it would have been him? And we have many other forms on the right hand side here. You can see a typical discoidal form. This is a very typical Ediacaran rock fossil from Britain. You might find things like this also in Newfoundland, and certainly this is more like the structure that we might get into a long argument about whether it's a fossil or whether it's just a concretion. Some people might call that Cyclomedusa, because originally some of these things were thought to be fossil jellyfish. I don't like that term because it's not really descriptive and it comes to a conclusion in its name. A conclusion we now know is incorrect. These are, I would use the Canadian term aspidella for these. That's what Elkanah Billings named these things in Newfoundland, in Canada. We now know that these are actually the holdfasts of these organisms. So related to Charnia and other things related to Charnia had a holdfast, and they were living upright, most of them, in the deep sea. around about 560 million years ago. So we know that some of these examples from Charnwood are just older than 562 million years, thanks to the work of Steve Noble and colleagues. And it's been a bit tricky to work out what these things are. It's reasonable to look at Charnia, and here we have a reconstruction of actually a Canadian Charnia that was put together by Martin Leicesters from the Czech Republic for the Oxford University Museum of Natural History, their first animals display. And you look at that, and it would be very reasonable to look at that and go, that's a leaf, that's a plant. But we know that it could not have been a plant. We know that these rocks, because of studying the sedimentology, were deposited in the deep sea. And in the deep sea, there is no light. We're well under wave base here. And if there's no light, you can't be an animal. And we know also, because of their alignment and other things, that these things were dying where they lived. They weren't plants from the shallow marine being washed in. So we can rule out the plants. But finding out what these things are has been a huge debate in paleontology for some time. And it's essentially, the problem comes, is they don't have many of the features that we would compare to modern day organisms. So even when you go down to the wren's nest and you find something a bit strange, it's at least got, you know, compound eyes and a few legs that's a bit similar to things in the day. So you can get down to at least phyla level of what the beasties are in the Silurian rocks of the Black Country. Whereas you look at this and you go, well, it hasn't got eyes or a mouth or a gut or legs or arms or feathers or, you know, leaves or anything like that. You know, how are we going to compare this thing to anything else? And really, that problem was solved by Dr. Frankie Dunn, who we're very pleased is now a senior research fellow at the Oxford University Museum of Natural History, and is going to be continuing her work there. She published a paper a few years ago that has fairly conclusively ended this debate and shown that Charnia is or was an animal. And one of the first things she did is she looked and took measurements from Charnia specimens in Charnwood Forest, in Newfoundland, in Canada, and also some of the Russian specimens. And she looked at how big they were and also their branches. You can see in my simplified cartoon diagram here that Charnias have this kind of branching structure. It's very kind of pseudo-fractal. As you zoom into it, it looks like there's a smaller Charnia on every branch that's branching off the previously bigger branch. And we have this characteristic zigzag shape of where the branches are branching off each other. And what she noticed was baby Charnias, and we do find specimens really quite small, only a few millimeters long, and we find some Charnias this big. And as she looked at how they were growing, she noticed that at first, Charnias grow by adding new branches. So when you find a tiny little baby Charnia, it will only have a few branches, and then you might find one this long, and it might have 20 branches. But it gets to a certain point in a Charnia's life when it stops adding new branches, and it then grows by simply inflating all the branches it's got. And Frankie tells us that this is a mode of growth, to have that kind of two-style growth with the transition in the middle. Only animals do that. That's something that we only find in the animal kingdom. So that's why not necessarily looking at the features, but how these things are growing has helped us. And so she also succeeded in doing some calculations to show where it sits within the animal tree. So in blue there, we've got all of the metazoa, the animals, going from the porifera, the sponges, all the way through to the ecdysozoa on the right-hand side. That's things that shed their external skeleton, things like insects and crabs and spiders. We are the chordates. which I've put as a deer because there are lots of deers in Charnwood Forest. And Frankie showed that Charnia is not only, this is based on a character-based matrix and very complex paleontological techniques, that shows us that it's not just an animal, but it is a eumetazoa. So all of the animals to the exclusion of the porifera and the placozoa. Placozoa, if you've ever come across the placozoa, probably not, because they're really, really weird and there aren't many of them. The main type of placozoa is called trichoplax, and it's basically a microscopic splat of cells. But it is an animal. And yes, so Charnia is here. So next to the ctenophores, and so ctenophores are an example of those is if you ever come across a sea gooseberry, so ctenophore, and then the cnidarians, which is jellyfish and corals. So really, really useful to get us to understand that actually the story of not only the animals but also the eumetazoa stretches back into Charnwood Forest and actually a little bit further in Newfoundland, because the oldest Charnias are in Newfoundland around about 574 million years ago. And that's really the only bit of my research that I'll mention tonight, because that was my bit of geochronology. And that's really important because it's telling us about not only the lead up to the Cambrian explosion, but also that there was, I would describe it, that there was this long ediacaran fuse that was burning of animal evolution up to the Cambrian explosion after 539 million years ago. So really, really useful. And what I'm going to show you now is a few new reconstructions, again done by, he's usually smiling more than this. This is Martin Leicestershire, very skilled paleo artist from Czechia. Lovely chap to work with. And Frankie and I have been working with him to bring these fossils to life. Most of the fossils in Charnwood Forest are preserved as impressions in the rock. So these were soft-bodied organisms. And so we find them preserved sometimes under layers of volcanic ash, and they're preserved as impressions in the rock. So there is no chemical difference between the bit of the rock that's a fossil and the bit of the rock next to the fossil that isn't a fossil. So all the information is in the shape of that fossil, or not fossil around it. So they can be quite difficult things to explain to people. Again, we can go and get a trilobite from the wren's nest, and you can show that to someone and they instantly go, oh, that looks a bit like this, or that looks a bit like that. Whereas when it's a squashed thing in the rock, it's much harder to tell the story. And that's why it's so important to work with people like Martin to bring these fossils to life. So that's what I'm going to show you now. And this includes some examples that have never had reconstructions done before, which is why we're so grateful to Martin for his work. So this is Charnia masoni, but of some examples given by from Charnwood Forest, and using some of the lessons that have been learnt in the last few years. You'll notice that we've got some branches coming off here, and if you want to know more about them, if you go and look at Frankie Dunn's paper where she writes about the previous work, it's in Science Reports, I think, if you want to look that up. I think, it's freely available online. So there's Charnia masoni, this frondose organism, soft-bodied, living at the bottom of the sea. And we're going to explore some of the wider groups, because you'll notice that some of the structures on here look a bit Charnia-like. We're getting those similar branching patterns again. This is Hylocolulus fordi, and again we're seeing here a holdfast disc at the bottom. So you could imagine that discoidal structure that I showed before could be the disc from a fossil like this, where we simply haven't preserved the stem and the fronds on top. And typically, Hylocolulus, these specimens can be about this big, and they have a stem, and then these frondose elements on the top, arranged in a kind of bowl-like structure. Of course, the colours that we've chosen are total guesswork. We pick ones that look nice and might be reasonable, but we have absolutely nothing to back up our choice of colours. So we just have to pick things that, you know, are reasonable, and we often look at what other marine organisms in the modern day, what colours they are. And we call these branching structures and the group of organisms that all have them rangiomorphs. I think they should have been called charniomorphs because Charnia came first, but they were named rangiomorphs after Rangia, which was in that same club of fossils and found in Namibia. So there's Hylocolulus fordi. We also have Primocandelabrum. They never pick easy names, my colleagues in Precambrian paleontology. So you can see, again, very Charnia-esque elements of these branching structures. Primocandelabrum, I should have said, Hylocolulus, only known from Charnwood Forest. Primocandelabrum, known from Charnwood Forest and also from Newfoundland, both from the Mistaken Point UNESCO World Heritage Site and also the Discovery UNESCO Global Geopark. Charnia discus concentricus, again we've got that hold-fast disc here, and this is one of those fun paleontological stories where part of the fossil was found first and described, and then they realised that the beast was a bit bigger than they thought. I don't know if you've ever come across the fossil Anomalocaris, which was first described in kind of 3 separate parts, and then they realised it was all part of the same beast. Well, Charnia discus concentricus was really first described just from the disc, and then someone noticed that it had a frond coming out of it. And again, these are known from around the world now, most prominently Charnwood Forest, and also from Charnia. This isn't from Charnwood. This isn't a rangiomorph. This is what we call an arboriomorph, and there are other arboriomorphs around the world, but it's got a clear central stem, which Charnia and others don't have. They have more of that zigzag stem, but this has a central stem and different elements, different types of branching coming off that. But another wonderful fossil that we've got. And then this is the weird one. So this was actually found many years ago, but was described and written up last year by Frankie Dunn and colleagues from the British Geological Survey. And you will note that it looks nothing like Charnia, and it looks nothing like Charnia discus, so it's not a rangiomorph, and it's not an arboriomorph. It's something totally different. This is found on the same slab as Hylocolulus and Primocandelabrum and Charnia and the original Charnia. They all come from, these particular examples all come from the same site. But you see it has this kind of goblet-like shape with tentacle-like structures coming out of the top. And that's why it's got its name Aurora Lumina. This kind of early torch is the rough translation. And recognising Attenborough's long interest and support for paleontology in Charnwood Forest, named after Attenborough himself, and that was released last year, and we're grateful to Martin for doing a reconstruction which we could now use to tell the wonderful story of this. No rangiomorph branching, tentacles at the top. The way this is kind of squashed onto the rock makes the researchers feel that there's possibility that there might have been some form of biomineralization that's now been lost, potentially. But looking at where this sits within the fossil tree, the tree of life, the researchers are fairly confident that this is the oldest predatory animal in the world, and that those tentacles, much like operating in a similar way to modern-day cnidarians, and anyone seen a kind of prawn make the wrong move, or shrimp make the wrong move in a rock pool and get grabbed by a sea anemone? It's reasonable to say that this was kind of dining out in a similar style Still lots to be understood about this. And again, what's quite interesting about this is the replica, the cast replica of all the fossils on this surface, which is about, the bit of the replica is about as big as that board there, has been on display in Leicester Museum for more than 5 years. They only published it last year. So this has been greeting people as they wander around Leicester Museum for some time. But it's great that we're still finding fossils in Charnwood Forest. And I really do hope that continues. And it's great to see that they're not just rangeomorphs, that there's a really interesting and diverse story about the early evolution of animals. And it really sets Charnwood Forest apart as a place that researchers who are interested in that story need to come to. So what I'm going to do to wrap up, I've got no idea for how long I've gone on for, is tell you a bit more about some of the wonderful things that we have that are nothing to do with the fossils, and just briefly go through those. And some of this I've already talked about, but we've got many rocks and stones that have been used in architecture, both locally but also around the country. Everything from our Markfieldite and also the Mount Sorrel granodiorite, which you can find in modern day, but also in Victorian streets around the country. If you go into some of the Victorian streets around Euston Station in London, you'll find many of these. Our fantastic gravestones here, you'll see that this quote that was put on this one from Anstey Graveyard, stand here frail stone, and yet it has stood the test of time 200 years later, still very legible. Some stones that were used from a local quarry and are only known in the buildings in that village. So for example, the Braggate Formation used to build some of the houses and the old school in the village of Woodhouse Eaves. And you can see some of the beautiful carving structure here in some of the Swidland slate. You can also find it next to the Albert Memorial, just next to Hyde Park. If you go around there, everything that is green, purple or grey is Swidland slate. And if you look very hard, you might be able to find a Tyche trace fossil that will tell you that it's from the Lower Cambrian, around about 530 million years old. Swidland slate, as I said, mostly used in roofs locally, but was also used in things more broadly. St Pancras Railway Station was originally roofed in Swidland slate because it was meant to be an expression of the places that you could visit if you were to board a train there. Unfortunately, when the place was done up, they got rid of the Swidland slate and replaced it with Cumbrian slate. Destroying my heritage. There we go. Here we go. There's that wonderful quarry, Barden Hill. So let me find you a scale. There's a 4x4 there that's about 3 pixels tall. That's Barden Hill, one of the largest quarries in the UK. Certainly before the pandemic, that would produce somewhere between 8 and 12% of the entire UK's aggregate need. So between 8 and 12% of every bit of crushed rock in the country comes from that one hole. And that's one of only 4. We have 4 major quarries in Charnwood Forest. And you can see the kind of grey, slightly purpley Precambrian igneous rocks at the base. That's the rock that they're mainly after. And then this V-shaped unconformity with the Triassic sandstone. My date's a bit out there. It's slightly older than 210 million years old, probably around about 230 million years old there. And these rocks are still used today, whether it's from Barden Hill or Cliff Hill or Whittick Quarry, which is being opened up again, or Mount Sorrel. These rocks underlie modern structures that we know: the new Wembley Stadium, the Olympic Park, the Shard, the M25, Heathrow Airport, the M1, Silverstone. They're all built using our rocks because we have the closest major source of hard rocks to London and the southeast. They only have pitiful, weak, Mesozoic, and even younger rocks than that. You can't build great structures to represent a nation on such tepid modern rocks. You need robust rocks from Charnwood Forest, and that's what we lend to the nation. We also have a great deal of mineral diversity, mineral geodiversity in Charnwood Forest. We're very appreciative to the Russell Society for the support that they give to us at the Geopark. And I believe I'm right in saying there's more than 100 minerals that you can find across Charnwood Forest. And I've just picked some of the nice shiny ones that we've got in the specimens at the Oxford University Museum of Natural History. So azurite and malachite and visinite and palygorskite. We have gold and silver. We even have a mineral that was first discovered in Charnwood Forest by one of the leading members of the Russell Society, and that is Bob Kingite, named after Bob King, the former professor at Leicester, who was very involved in mineralogy and the Russell Society. So very, very appropriate, and has since gone to be found all around the world, but it was first found in Charnwood Forest. And of course, just our quarrying history as well. Here's a picture of Hill Hole, just next to Markfield. So one of the original sites of where Markfield was quarried from, sometimes referred to as a Markfield Knoll. This is now a nature reserve and a brilliant example of how geodiversity, even geodiversity that's been revealed by man-made processes, and by geodiversity I mean the variety of the non-living elements of nature, influence biodiversity. Because this flooded, this is now flooded to right up to about here. And it's a nice nature area where people go for a walk, and hopefully in a year's time they'll also come and think about rocks. It's also a haven for the native crayfish, because that giant pool of beautiful water is cut off from the watercourses. So the invasive crayfish and the plague that it carries never gets in. So it is, geodiversity is providing a beautiful haven for biodiversity. And I think it's important that we make our biological friends realise the influence that geology, even when it's created, the shape of it, the morphology of it is created by man-made processes. I think it's important that we remind our biological colleagues of the influence that geodiversity plays, and they would be nothing without us. And our rocks have started to travel around the world. We're very grateful to the Melodal Natur and Park, UNESCO Global Geopark in Luxembourg, where there's a lovely lump. There's that speckledy appearance there of Markfieldite, which is on display in the Wall of Geoparks in Luxembourg. So if you're ever over there, do go and see Connie and the team, because there's rocks from all around the world there, and we're very proud that there's a little lump of Leicestershire down in Luxembourg. I also want to show you how our landscapes, because that's part of our geodiversity as well, have influenced art. The Leicester art scene goes back for many years. Here's Ravenhill, which is part of Bradgate Park, painted by Edward Davies, a leading member of the kind of Leicester art scene of the day. We also have Laborare Est Orare, which is in the Tate Gallery. In the background here, you can see Mount St Bernard's Abbey, the only Cistercian abbey in England and the only brewer of Trappist ale in England. So get yourself a glass of Tint Meadow. It's very, very nice, and we're very glad that we've got a brewer in our geopark. And here you can see the monks at work in the fields around the abbey in 1862, and those characteristic crag-topped upland-style areas of Charnwood Forest. Here's John Fernley with archery meeting at Bradgate Park in 1850, which is now held in America at the Yale Centre for British Art. John is really regarded as the greatest painter, British painter of horses of all time. If you were a Victorian and you had some horses, it was really the done thing was to get John down and have him paint your horses. And clearly the people at Bradgate Park did well there. And John paints a number of different scenes. And in the background, you can see this is our major landmark. This is Old John Tower, a little tower that was built to watch the deer hunting in Bradgate Park. And Peter de Wint, Barden Hill. Barden Hill is what is now has the, you can still see that same shape in the landscape today. If you drive up the M42 and look off to the right, you will see Barden Hill in the distance. It's 278 metres above altitude and the highest point in Leicestershire, the 23rd highest county top in the UK, and only, I think we're 1 metre behind, was it Wiltshire? So I might do a kind of Englishman who goes up a hill and comes down a mountain and start piling up rocks on the top of Barden Hill. But the one I like the best is Barden Hill, painted from Culloden, also now owned by the Yale Centre for British Art, painted by a very famous artist, John Constable. He was fairly pally with the people who owned the house at Culloden and would go out there and paint. So this is from outside the geopark, and that characteristic shape of Barden Hill. The quarry sits kind of just round the corner from that. So luckily the quarry has not affected that beautiful landscape. And so just to wrap up, what are we on about? Why do we want to make a geopark out of this? Well, I hope I've showed you that we've got something really special in Charnwood Forest. We've got some very important rocks that are telling a unique story that's important to our understanding of Earth history, and that we can use that to further influence our understanding of the geological sciences, and also for the benefit of education and educating a new generation of geoscientists. What we're aiming to do by bringing together all these partners, including the British Geological Survey, local government, the National Forest, the NFU, arts groups, access groups and regulators, is we're working on a 5-year project, which we're now about halfway through, funded by the National Lottery Heritage Fund. And our aim is that a UNESCO Global Geopark is the major legacy of our project. Not everything we do is all about rocks. It's about building a holistic program that has rocks at its centre, but has an education program, has an arts program, has a business development program, because this has to serve the benefit of all the communities we have in Charnwood Forest. And so as we go about our journey, it's really helpful to have the friendship of places like the Black Country UNESCO Global Geopark and the assistance of people like Graham, who you can very easily knock on the door of and say, what did you do when this came up? So we're very, very grateful for that. And there you've got just a flavour of, I basically put this slide up to show, we've got lots of projects and we're doing lots of things, and it's not all me looking after rocks. And I don't know how much Graham has fully indoctrinated you in the world of UNESCO Global Geoparks, but I think it's good to reflect on where they are around the world, and that UNESCO is looking for somewhere that has internationally significant geology and that uses it to sell the story of geosciences, to promote education, and importantly for sustainable economic development. And that's also a reason why we're interested in when we have things like lovely breweries, because you've got a great story of people coming in and they can have an enjoyable drink, and maybe they can learn a bit about how the geology has influenced that taste or that style of beer. We also have, I should say, a vineyard. You might not associate Leicestershire or Charnwood Forest with a vineyard, but we have a vineyard in Charnwood Forest. And these are some of the wonderful places all around the world that are UNESCO Global Geoparks. There's about 190 now, with another 10 dozen on the way in probably May time. So we've got Lanzarote, Burren and Cliffs of Moher in the Republic of Ireland, for the wine drinkers in the room, Beaujolais. If you want to go to the kind of the biodiversity capital of the world, some would say, the Ngorongoro Lengai region of Tanzania. Reykjanes in Iceland, very famous a few years ago for those constant live streams of the volcanic sticky lava, basaltic lava being erupted there. These are some of the places around the world. Hong Kong. And you're all invited. Because later this year, we're hosting, very pleased to be hosting, ProGeo, which is an international organisation which very cleverly recognises that its name is a bit of a mouthful. So we just call ourselves ProGeo. The full name the International Association for the Conservation of Geological Heritage. We're very pleased to be hosting the 11th symposium for 3 days in October. You can find more detail at progeo2023.com. And for those 3 days, there's going to be lots of discussions about geoheritage, about conservation, geotourism, how do we look after sites. The great and the good of the world are coming. They're all booking in, and it's on your doorstep. You don't have to go to, you don't have to fly abroad. You just pootle on down to Charnwood Forest and join us for there. There's special rates. It's cheaper if you join, but even when you combine the fee of joining the association, it's still much cheaper to go for that route. So do have a look at that. There are also field trips. You probably won't want to go on the pre-conference field trip, not because it's led by Graham, but because it's coming here. So the pre-conference field trip on the 8th is led by Graham and Colin Prosser, and he's coming here to explore for a day the wonderful geology of the Geopark here. And then from the 12th to the 14th, you can come on a 3-day mega field trip to explore all of the sites in Charnwood Forest with a bit of behind the scenes, places that we wouldn't normally go. So if you really want to see some of these places, do let us know. We're going to go to the British Geological Survey as well, and they're going to get out the great master casts of the fossil surfaces. So we'll have an hour or two there looking at those great paleontological resources. So yes, we add to a list of host cities that includes Rome and Reykjavik and Dublin. We add Loughborough. So yes, do come and join us. You'd be most welcome. And all I'd say, if you want to find out more, we are on social media. Our website will be going live soon. We have guided walks. There's going to be lots of big surge in new interpretation later this year, and you would all be most welcome, either individually or if you ever wanted to come as a group to see Charnwood Forest. We'd love to show you around. So I think at that point I have probably gone on way too long, but I'd be happy to take any questions if there's time.
Thank you very much, Jack, for not only a wonderful, clear, well illustrated talk with some wonderful new stuff being illustrated here, but also thank you again for the offer to bring our society to come and see the potential geopark and what's in store in the future. So if there's no other questions, no other comments, can I ask you all to join me in thanking Jack in the usual way?
Thank you. Cheers.